Welcome, and thank you for joining us on this journey through the cosmos. As you settle in and let your mind drift among the stars, we invite you to explore the wonders of our home galaxy, the Milky Way. Let these facts wash over you like gentle waves, each one a small window into the vast universe we inhabit. There's no need to focus too intently, just allow the words to carry you peacefully through the night as we wander together through space and time. Take a deep breath, relax, and let yourself float among the countless stars that make up our cosmic neighborhood, each one a sun with its own story to tell. The Milky Way appears from Earth as a hazy band of light stretching across the night sky, a sight that has captured human imagination since our earliest ancestors first looked upward into the darkness. This luminous ribbon arcs overhead like a celestial bridge, connecting one horizon to the other in a graceful sweep that has inspired countless stories, myths, and scientific inquiries throughout human history. On a clear night, far from the glow of city lights, this band reveals itself in stunning detail, a river of soft light that seems to flow through the darkness. The experience of seeing it truly clearly, without light pollution dimming its beauty, is one that connects us directly to our ancient past, when every culture on Earth knew this sight intimately and wove it into their understanding of the cosmos. For those who live in modern cities, the Milky Way has become almost invisible, hidden behind a veil of artificial light that brightens our nights but obscures the stars. Yet in remote locations, on mountaintops, in deserts, or far out at sea, the Milky Way still reveals itself in all its glory, reminding us of what our ancestors saw every single clear night of their lives. The realization that this glowing band is actually our view from inside a vast disk of stars, looking edge-on through billions of distant suns, adds layers of meaning to this ancient sight. Ancient cultures across more than 30 constellations noticed this glowing band, brightest toward Sagittarius, where the galaxy's core lies hidden behind vast clouds of dust and gas. These observers, scattered across every inhabited continent, recognized that something special resided in this direction, even without telescopes or modern instruments to guide them. The concentration of light toward Sagittarius created a bulging brightness that ancient stargazers could clearly perceive, and they understood that this region held particular significance in the structure of the heavens. The core itself remains invisible to optical telescopes from Earth, shrouded by immense clouds of interstellar material, but its gravitational influence and the density of stars surrounding it make the region unmistakably brighter and more crowded with stellar light. This brightness drew the attention of cultures worldwide, who often placed their most important celestial stories and seasonal markers in this region of the sky. The fact that so many different cultures, separated by vast distances and developing independently, all noticed and attributed significance to this particular region speaks to the fundamental human drive to observe and understand the patterns in nature. These ancient astronomers possessed remarkable observational skills, tracking subtle changes in the sky's appearance through the seasons and over years, building up knowledge that was preserved in oral traditions, monuments, and eventually written records. The Milky Way's name comes from Greek mythology, where Heros' spilled milk formed the glowing trail in the sky, a story that speaks to humanity's eternal need to understand the cosmos through narrative and metaphor. The term quantum refers to discrete packets of energy rather than continuous values. Imagine pouring water from a container, and the flow appears smooth and uninterrupted. In the world we experience with our senses, energy seems to flow this way, continuously and infinitely divisible. But at the quantum scale, energy doesn't flow smoothly at all. Instead, it comes in specific, indivisible chunks, like coins in specific denominations rather than an infinitely divisible stream of value. These discrete packets, or quanta, represent the smallest possible units of energy that can exist for any given phenomenon. You cannot have half a quantum, just as you cannot have half a photon. This discreteness is fundamental to the fabric of reality itself, not just a limitation of our measurement tools. The universe, at its most basic level, is granular rather than smooth, digital rather than analog in a sense, though this comparison only goes so far. This quantum nature of energy has profound implications for everything that exists. Classical physics fails to explain atomic stability, radiation, and microscopic behavior. For centuries, the physics developed by Newton and Maxwell worked beautifully to describe the motion of planets, the behavior of machines, and the propagation of light and electromagnetic waves. But when scientists at the turn of the 20th century tried to apply these classical laws to atoms and the radiation they emit, they encountered profound contradictions. According to classical electromagnetic theory, an electron orbiting an atomic nucleus should constantly radiate energy as it accelerates in its curved path, just as radio transmitters emit electromagnetic waves from accelerating charges. This radiation should cause the electron to lose energy continuously, spiraling into the nucleus in a tiny fraction of a second. Yet atoms are stable. They don't collapse. Matter exists. Classical physics also predicted that heated objects should radiate infinite amounts of energy at high frequencies, an absurdity known as the ultraviolet catastrophe. These failures weren't minor discrepancies that could be smoothed over with small adjustments. They were fundamental breakdowns that revealed classical physics, for all its successes, was incomplete. Something entirely new was needed to understand the atomic world. Max Planck introduced energy quanta in 1900 to explain blackbody radiation. When objects are heated, they glow, emitting light whose color depends on temperature. A blackbody is an idealized object that absorbs all radiation falling on it and emits radiation based purely on its temperature. Planck was trying to derive a formula that matched experimental measurements of this radiation across all wavelengths. The classical approaches kept producing nonsensical results, including that prediction of infinite energy at short wavelengths. In what Planck himself later called an act of desperation, he made a radical assumption. Perhaps the energy of electromagnetic oscillators in the walls of a heated cavity could only take on certain discrete values, rather than any value whatsoever. He proposed that energy came in packets, with each packet having an energy equal to the frequency of oscillation multiplied by a new fundamental constant, now called Planck's constant. This assumption, seemingly arbitrary but mathematically necessary to fit the data, worked perfectly. The formula Planck derived matched observations with remarkable precision. Yet even Planck didn't initially realize the full implications of his quantum hypothesis. He thought of it as a mathematical trick, a useful fiction. It would take Einstein to recognize that energy quantization was a deep physical reality. According to the myth, the infant Heracles was placed at Hera's breast while she slept, and when she awakened and pulled away, her milk sprayed across the heavens, creating the luminous band we see today. This story connected the earthly and familiar, the nourishing milk that sustains life, with the mysterious and distant realm of the stars. The Greeks understood that names and stories helped make the incomprehensible more approachable, transforming the vast and alien sky into something woven into human experience. Such myths were not primitive attempts at science, but rather poetic frameworks that allowed ancient peoples to organize their observations and pass down knowledge through memorable tales that would survive generations. The milk metaphor carried deep symbolic meaning as well, suggesting that the heavens themselves provided nourishment, perhaps spiritual or intellectual rather than physical, feeding the human soul's hunger for understanding and connection to something greater than everyday existence. These stories also served social functions, providing shared narratives that bound communities together, giving people common reference points and a shared cosmology that helped define their culture's worldview and place in the universe. Romans called it the Milky Road, while Greeks called it the Milky Circle, the root of the word galaxy, which comes from the Greek word galaxies, meaning milky. These ancient names reveal how different cultures perceived the structure differently based on how it appeared in their skies at different latitudes and seasons. The Roman term Via Lactea, or Milky Way, emphasized the band's appearance as a path or road stretching across the heavens, perhaps suggesting a route for souls or gods to travel between the mortal world and the divine realm. The Greek term emphasized its circular nature, recognizing that the band forms a complete ring around the celestial sphere, even though only portions are visible at any given time depending on season and location. This linguistic heritage reminds us that our modern scientific terminology often carries within it thousands of years of human observation and wonder, each word a small time capsule containing the thoughts of our distant ancestors as they contemplated the same sky we see today. The evolution of language around astronomical concepts shows how human understanding gradually deepened, with each generation adding its own observations and insights to the accumulated wisdom of the past. When we use the word galaxy today, we unconsciously invoke this entire history, carrying forward the observations of people who lived thousands of years ago and found in the night sky both beauty and mystery worthy of their most careful attention and most creative storytelling. In Chinese tradition, it is known as the Silver River, while in Sanskrit it is called Akash Ganga, the river of the heavens, names that emphasize the flowing, water-like quality of the Milky Way's appearance. The Chinese name, Yin He, evokes the shimmering quality of starlight that resembles sunlight glinting off flowing water, creating a celestial parallel to the great rivers that shaped Chinese civilization and provided the foundation for agriculture, trade, and cultural development. In Chinese mythology, this silver river separates two lovers, the weaver girl and the cowherd, who can only meet once a year when a bridge of magpies forms across the sky, a story celebrated during the Chishi festival that honors faithful love and the endurance of separated hearts. The Sanskrit name Akash Ganga directly references the sacred Ganges River, suggesting that just as the earthly Ganges flows with purifying water that washes away sins and grants spiritual merit, the celestial river flows with divine light that illuminates the darkness and connects the earthly realm to the heavens above. These aquatic metaphors appear across many cultures, perhaps because the Milky Way's soft, diffuse glow and flowing shape naturally recall the movement and shimmer of water, one of the most vital and omnipresent elements in human experience. Water flows, water sustains life, water reflects light, and in all these ways it provides a perfect metaphor for understanding the mysterious glowing band that flows across the night sky, seeming almost liquid in its soft luminescence and graceful arc from horizon to horizon. The Cherokee described it as cornmeal spilled by a fleeing dog, calling it the way the dog ran away, a story that speaks to both humor and practical observation in indigenous astronomy. According to Cherokee tradition, a dog stole cornmeal from a gathering of people in the south, and as it ran away toward the north, the meal spilled from its mouth, creating the glowing trail across the sky that we see today. This story not only explained the appearance of the Milky Way but also encoded practical astronomical information, as the Milky Way's orientation in the sky indeed runs generally north-south as visible from Cherokee territories, providing a useful navigational reference for travelers and hunters. The tale demonstrates how indigenous peoples often embedded navigational and seasonal information within their myths, creating stories that were simultaneously entertaining, educational, and scientifically useful for their communities. Such stories were teaching tools, passed from elders to children, ensuring that astronomical knowledge survived through generations without need for written records, carried forward in the collective memory of the people through engaging narratives that made the information easy to remember and pleasant to retell. The choice of cornmeal as the substance spilled by the dog connected the story directly to Cherokee agricultural life, where corn served as a staple crop of tremendous importance, making the story resonate on multiple levels, linking the heavens above to the fields below and the daily sustenance that kept the people alive and thriving. Australian Aboriginal Gomero people see the dark dust lanes as the giant emu in the sky, a striking example of how some cultures focus not on the bright stars but on the dark spaces between them, demonstrating a sophisticated understanding that what appears to be absence can itself form meaningful patterns. This celestial emu is formed by the dark nebulae, massive clouds of dust that block the light of stars behind them, creating dark patches against the bright background of the Milky Way. The emu's head, body, and legs can be traced through these dark lanes, and the figure appears to change orientation throughout the year as Earth's rotation carries different perspectives into view, with the emu standing upright at certain times and lying on its side at others. The visibility of the celestial emu marks important seasonal changes for the Gomero people, indicating times for gathering emu eggs and other significant activities in their annual cycle, connecting the patterns in the sky directly to survival and sustenance on the land below. This demonstrates a sophisticated understanding of positional astronomy, using the darker features of the night sky as a kind of shadow calendar that guided practical decisions about food gathering and cultural ceremonies, timing hunts and harvests to align with celestial signs that had been proven reliable over countless generations. The recognition that darkness itself could form patterns worthy of attention speaks to a different way of seeing, one that looks not only at what is present but also at what is absent, understanding that both light and shadow work together to create the full picture of reality. Galileo Galilei first resolved the Milky Way into individual stars with a telescope in 1610, a discovery that fundamentally transformed humanity's understanding of the cosmos. Before Galileo turned his improved telescope toward the Milky Way, the prevailing belief was that it might be some kind of luminous gas or atmospheric phenomenon, perhaps something akin to aurora or unusual weather effects projected into the higher reaches of the atmosphere. When Galileo observed it through his relatively simple telescope, magnifying the view by only about 20 or 30 times, he saw that the hazy glow resolved into countless individual points of light, stars too numerous to count and too faint to see with the naked eye alone. He described his observations in his book Sidereus Nuncius, or Starry Messenger, writing with evident wonder about the discovery that what appeared as clouds or mist was actually composed of more stars than anyone had imagined existed, multiplying the known population of the heavens many times over in a single observation. This observation was one of several that year that revolutionized astronomy, alongside his discoveries of Jupiter's moons proving that not everything orbited Earth and the phases of Venus demonstrating that Venus orbited the Sun, all of which challenged the Earth-centered model of the universe that had dominated Western thought for over 1,000 years. The simple act of pointing a telescope at the Milky Way and sharing what he saw with the world helped begin the process of revealing just how vast and populated the universe truly is, a process of discovery that continues to this day as each generation of more powerful instruments reveals ever deeper layers of cosmic structure and complexity. Democritus had proposed as early as 460 BC that the Milky Way was made of distant stars too faint to see individually, demonstrating that careful reasoning and keen observation could lead to correct conclusions even without technological instruments to confirm them. This ancient Greek philosopher, known primarily for his atomic theory of matter, which proposed that all substance was composed of tiny, indivisible particles called atoms, applied similar logic to the heavens, suggesting that just as matter was made of invisible atoms whose combined properties created the visible substances we experience, the Milky Way might be made of invisible stars whose combined light created the visible glow stretching across the sky. His proposal was based on observation and inference rather than direct evidence, but it showed remarkable intuition about the nature of light and distance and the way that many small sources can combine to create what appears to be a continuous glow. For nearly 2,000 years his idea remained unproven speculation, neither accepted nor completely rejected by the astronomical community, existing in that uncertain space where an idea seems plausible but lacks definitive evidence to establish it as fact. The idea circulated among scholars, appearing in various texts and discussions, sometimes endorsed and sometimes dismissed, until Galileo's telescope finally provided the visual evidence that confirmed what Democritus had reasoned so long ago through pure thought and observation. This long gap between hypothesis and confirmation reminds us that scientific truth sometimes requires both insight and the right tools to reveal itself, and that human reason, while powerful, benefits enormously from the ability to test ideas through observation and experiment. For centuries afterward, many believed the Milky Way was the entire universe, that these countless stars revealed by telescopes represented all of creation, and that nothing existed beyond this great wheel of light spinning through the void. This seemed a reasonable conclusion given the evidence available at the time, as telescopes revealed more and more stars within the Milky Way but showed nothing clearly beyond it. Astronomers could see fuzzy patches called nebulae scattered here and there among the stars, but most believed these were clouds of gas within our own stellar system, perhaps places where new stars were forming from the cosmic material that filled the spaces between existing stars. The idea that the universe might be larger than the Milky Way seemed unnecessary and perhaps even philosophically troubling, as it implied vast regions of empty space between separate stellar systems, an apparent waste of space that seemed inconsistent with ideas about divine efficiency and purpose in creation. This geocentric view of the galaxy, with Earth near the center of the only stellar system in existence, persisted well into the 20th century, and debates about the true nature of spiral nebulae continued for decades before being finally resolved, with passionate arguments on both sides about whether these fuzzy spirals were nearby clouds within the Milky Way or distant island universes, each containing billions of stars of their own. That view changed in 1923 when Edwin Hubble resolved stars in Andromeda, proving other galaxies exist and that the universe was far larger than anyone had imagined, expanding the scale of creation almost beyond human comprehension. Using the powerful Hooker telescope at Mount Wilson Observatory in California, at that time the largest telescope in the world with a mirror 100 inches across, Hubble identified Cepheid variable stars in what was then called the Andromeda Nebula. Cepheid variables are stars whose brightness changes in regular, predictable patterns, pulsating in and out over periods ranging from days to months, and astronomers had discovered through careful study that the period of these variations directly relates to the star's true luminosity, with longer period Cepheids being intrinsically brighter than shorter period ones. By comparing how bright these Cepheids appeared in the sky with how bright they should actually be based on their pulsation period, Hubble could calculate their distance using the inverse square law of light, and the answer was shocking and paradigm-shattering. Andromeda lay nearly 1 million light-years away, far beyond the accepted boundaries of the Milky Way, which was thought to extend perhaps 100,000 light-years across, proving conclusively that Andromeda was a separate galaxy entirely, not a nebula within our own system but a stellar system comparable in size to the Milky Way itself. This discovery, announced in a paper that would transform cosmology and establish Hubble's reputation as one of the great astronomers of the 20th century, meant that the universe contained potentially billions of galaxies, each containing billions of stars, expanding the scale of creation almost beyond comprehension and making humans seem smaller and more peripheral than ever before in the cosmic scheme. Today we know the Milky Way is a barred spiral galaxy containing the Sun and Earth, one galaxy among hundreds of billions scattered through the observable universe, each one a vast stellar system in its own right. The term barred spiral refers to the elongated bar-shaped structure of stars that extends from the galactic center, with spiral arms curving outward from the ends of this bar in graceful sweeping arcs that trail through space like water swirling down a drain. Our Sun resides in one of these spiral arms, specifically in what's called the Orion Arm or local spur, about halfway out from the center to the edge, orbiting the galactic core in a journey that takes roughly 225 to 250 million years to complete once around. From our position within the galaxy, we see it edge on as that familiar band of light stretching across the sky, but if we could somehow view it from above, we would see a magnificent spiral pattern. Understanding our place within this structure took centuries of careful observation and mapping, plotting the positions of stars and gas clouds to gradually reveal the hidden architecture of our cosmic home, a task made challenging by our position within the structure we're trying to map, like trying to understand the layout of a vast city while standing in the middle of it with no ability to rise above and see the overall pattern. It spans roughly 100,000 to 200,000 light-years across, though defining the exact edge of a galaxy proves more difficult than it might seem at first consideration. A light-year, the distance light travels in 1 year at its constant speed of 186,000 miles per second, equals about 6 trillion miles or nearly 10 trillion kilometers, making the galaxy's diameter so vast that human minds struggle to grasp the scale in any intuitive or visceral way. If we could shrink the Sun to the size of a grain of sand, the Milky Way would still stretch thousands of miles across, and even that comparison fails to fully convey the emptiness and vast distances involved. The uncertainty in the galaxy's size comes from the fact that it doesn't have a sharp edge where stars simply stop appearing, no clear boundary like a coastline separating ocean from land. Instead, the density of stars gradually decreases as you move outward from the center, thinning out slowly until individual stars drift in the space between galaxies, becoming harder and harder to distinguish from truly intergalactic stars that don't belong to any particular galaxy. Recent discoveries have found stars and clusters much farther out than previously thought, extending the galaxy's reach and making astronomers continually revise their estimates of where the Milky Way truly ends and intergalactic space begins, blurring the boundary between what's inside the galaxy and what lies beyond it. Its visible disk is only about 1,000 light-years thick despite its enormous width, making the Milky Way shaped somewhat like two fried eggs placed back to back, or perhaps a pair of cymbals with a bulge in the middle, a flattened structure that results from fundamental physical processes. This extreme flatness results from the galaxy's rotation, which creates a flattened disk just as a pizza maker's spinning dough flattens into a circular shape under centrifugal force, with material naturally settling into the plane of rotation where motion is most stable. The central bulge, where stars orbit in more random directions rather than in the organized rotation of the disk, makes the galaxy thicker in the middle, creating that bulging profile that resembles the yolk of a fried egg rising above the flattened white surrounding it. Within this relatively thin disk, stars, gas, and dust orbit in roughly the same plane, creating the dense concentration of matter we see as the bright band across our sky when we look along the plane of the disk. The thinness of the disk means that when we look toward the galactic plane, we see vast numbers of stars stretching into the distance, thousands upon thousands of them crowding our view, while when we look perpendicular to the disk, upward or downward out of the galactic plane, we quickly see beyond the galaxy into the emptier intergalactic space where other galaxies float in the distance like islands in an infinite ocean. The galaxy formed about 13 to 13.6 billion years ago, nearly as old as the universe itself, which came into existence some 13.8 billion years ago with the Big Bang, that moment of unimaginable density and heat from which all matter, energy, space, and time itself emerged. This means the Milky Way assembled relatively early in cosmic history, in an era when the universe was younger, denser, and quite different from today. The galaxy didn't form all at once in a single moment of creation, but rather grew over time through a process of merger and accretion, with smaller clumps of matter gradually coming together under gravity's inexorable pull, building up from smaller proto-galaxies into the massive structure we see today. The oldest stars in the Milky Way, found primarily in the galactic halo surrounding the disk and in the ancient globular clusters that orbit the galaxy like satellites, date back to this ancient era and contain fewer heavy elements than younger stars because they formed before many generations of stellar death and rebirth had enriched the cosmos with elements heavier than hydrogen and helium. Studying these ancient stars is like archaeological work, reading the history of the galaxy written in the chemical composition and motion of these stellar fossils, each one a witness to the galaxy's early days and a record of conditions in the ancient universe. It contains roughly 100 to 400 billion stars, though counting the stars in an entire galaxy proves remarkably challenging even with modern technology and sophisticated statistical methods. The uncertainty in this number comes from several factors, including the difficulty of observing stars in regions blocked by dust which absorbs visible light and hides whole sectors of the galaxy from our view, the challenge of detecting the faintest and smallest stars which contribute to the total count but produce so little light they're almost impossible to see individually across galactic distances, and the complex process of extrapolating from the regions we can observe directly to the entire galaxy whose full extent we cannot survey completely. Astronomers use various methods to estimate this number, including counting stars in representative regions and scaling up based on the galaxy's total extent, measuring the total light output of the galaxy and dividing by the average star's brightness to infer how many stars must exist to produce that much light, and modeling how gravity from observed matter affects the motion of gas and stars to calculate how much stellar mass must be present. Each method has limitations and uncertainties, sources of error that can compound and make the final estimate imprecise, leading to the wide range in estimates that spans a factor of 4 from lowest to highest. But all methods agree that the number is measured in hundreds of billions, a quantity so large it becomes abstract, impossible to visualize or truly comprehend in any meaningful way. A number that exists more as a concept than as something we can genuinely grasp with our finite human minds. Red dwarf stars dominate the population, making up about 75% of all stars, yet these modest stars often go unnoticed because of their dim light and unassuming nature. Red dwarfs are small, cool stars with only a fraction of the Sun's mass and brightness, some producing less than 1/10,000th the Sun's light output, making them incredibly difficult to detect across the vast distances of space. Their faintness means that not a single red dwarf is visible to the naked eye from Earth, despite being the most common type of star in our galaxy. So when we look at the night sky with our eyes alone, we're seeing only the rare bright stars, the exceptional ones that are massive or nearby enough to register on our retinas, while the vast majority of stars remain invisible to us. These stars burn their hydrogen fuel so slowly and efficiently that they can shine for trillions of years, far longer than the current age of the universe, which is less than 14 billion years old, meaning that every red dwarf ever born still exists today, still shining faithfully in the darkness, none having yet reached the end of its immensely long life. Their longevity and abundance make them fascinating targets in the search for habitable planets, as any worlds orbiting red dwarfs have enormous spans of time for life to potentially develop and evolve, timescales that dwarf the few billion years life has had on Earth, raising intriguing questions about what forms of life might exist on ancient worlds that have orbited these patient stars for tens or even hundreds of billions of years into the deep future that lies ahead. The Milky Way may host at least as many planets as stars, potentially trillions, a realization that has emerged only in recent decades as astronomers develop techniques to detect planets around other stars and systematically survey the galaxy for these worlds. Beginning in the 1990s with the first confirmed detections of exoplanets, and accelerating dramatically with space-based missions like Kepler and TESS, astronomers have now confirmed thousands of exoplanets and identified thousands more candidates. Statistical analysis of these discoveries suggests that planets are the rule rather than the exception, with most stars hosting at least one planet and many hosting multiple worlds in complex systems reminiscent of our own solar system. This means that the Milky Way teems with planets of every imaginable variety, from hellish worlds orbiting close to their stars where surface temperatures reach thousands of degrees to frozen realms in the outer darkness, from rocky terrestrial planets similar to Earth to massive gas giants that dwarf Jupiter, from lonely wanderers drifting without stars to members of complex multi-planet systems like our own where numerous worlds orbit in gravitational harmony. More massive stars outweigh the smaller ones in total mass, giving the galaxy about 160 billion solar masses in stars, even though these massive stars are far less numerous than their smaller cousins. A solar mass is the mass of our Sun, a unit astronomers use because it provides a convenient reference point for measuring stellar and galactic masses without resorting to incomprehensibly large numbers. While red dwarfs vastly outnumber massive stars, a single blue supergiant can weigh as much as 100 or more red dwarfs, meaning the massive stars contribute disproportionately to the galaxy's total stellar mass despite being relatively rare. These massive stars live fast and die young, burning through their fuel in mere millions of years compared to the trillions of years a red dwarf can shine. When they die, they often explode as supernovae, catastrophic detonations that briefly outshine entire galaxies, seeding the surrounding space with heavy elements that will become part of future generations of stars and planets, contributing the carbon in our bodies, the oxygen we breathe, the iron in our blood, all forged in stellar furnaces and scattered into space by these cosmic explosions. The balance between numerous faint stars and rare bright ones creates the galaxy's overall luminosity profile and determines how quickly it converts gas into stars, regulating the pace of star formation and the galaxy's evolution over cosmic time. The luminous matter we can see accounts for only about 5% of the galaxy's total mass, a startling fact that reveals how much of the universe remains mysterious and invisible to our instruments, hidden from even our most sophisticated telescopes. The remaining mass comes from dark matter, a form of matter that doesn't emit, absorb, or reflect light or any other form of electromagnetic radiation, making it completely invisible to telescopes but detectable through its gravitational effects on visible matter which we can observe and measure. Astronomers first realized dark matter existed by measuring how fast stars and gas orbit within galaxies, discovering that they move much faster than they should if only visible matter provided the gravity holding them in orbit. The only explanation is that vast amounts of invisible matter must exist throughout the galaxy and beyond, providing the additional gravity needed to explain the observed motions and preventing stars from flying off into intergalactic space as they whirl around the galactic center. What dark matter actually consists of remains one of the greatest unsolved mysteries in physics, with candidates ranging from exotic subatomic particles to primordial black holes, but despite decades of searching, its true nature continues to elude us, a humbling reminder that for all our knowledge, we still understand only a small fraction of what makes up our galaxy and the universe beyond. A massive dark matter halo surrounds the Milky Way, extending up to 1 million light-years across, an invisible sphere of mysterious matter that dwarfs the visible galaxy and holds it in a gravitational embrace. This halo isn't made of anything we can see or touch, just this enigmatic substance that makes its presence known only through the way it pulls on things we can observe. The halo extends far beyond the visible disk and bulge, reaching out into the space between galaxies, creating a vast gravitational well within which the visible components of the galaxy reside like a coin at the bottom of a deep well. Within this enormous halo, the visible galaxy is almost like a small decoration, the bright and active center of a much larger structure that remains hidden from our eyes but not from our calculations. The discovery that galaxies exist within these massive dark matter halos fundamentally changed our understanding of cosmic structure, revealing that what we see when we look at galaxies is only the tip of the iceberg. The halo isn't uniform either, with computer simulations suggesting it as structure and substructure, clumps and streams of dark matter moving through it, remnants of smaller dark matter halos that merged with the Milky Way's halo over billions of years. Understanding the size and shape of this halo helps astronomers understand how the Milky Way formed and how it interacts with its neighbors, providing the gravitational framework within which the visible galaxy took shape and continues to evolve. More than 90% of the galaxy's mass is inferred to be dark matter, meaning that everything we can see represents only a small fraction of what's actually there. This ratio astonishes many people when they first learn it, the realization that the universe is dominated by something we cannot directly detect, that the matter we're made of and everything we've ever touched or seen represents only a tiny minority of what exists. This has profound implications for our understanding of what the universe is made of, forcing us to accept that the periodic table of elements represents only a small subset of the cosmic inventory. Dark matter doesn't participate in chemistry, doesn't form molecules, doesn't emit light, doesn't do any of the things that regular matter does, yet it shapes the structure of the universe through its gravity, determining where galaxies form and how they evolve over cosmic time. This dark matter explains why the galaxy's rotation speed stays flat far from the center, a phenomenon that puzzled astronomers for decades before the dark matter hypothesis provided an explanation. In our solar system, planets farther from the Sun orbit more slowly than those closer in, following Kepler's laws which describe how orbital velocity decreases with distance from the central mass. Astronomers expected galaxies to behave the same way, with stars farther from the galactic center moving more slowly in their orbits, but observations revealed something different and unexpected. When astronomers measured the rotation speeds of stars and gas at various distances from the galactic center, they found that the speeds remained roughly constant far out into the galaxy's outer regions. This flat rotation curve, as it's called, indicated that mass continues to increase with distance even where visible stars thin out and eventually disappear, suggesting that some invisible mass extends far beyond the visible disk. The dark matter halo provides exactly this distribution of mass, extending to great distances and providing the gravitational pull necessary to keep outer stars moving at higher speeds than they would if only visible matter were present. Without dark matter, the outer regions of galaxies would rotate so slowly that the observed speeds would fling stars out into intergalactic space, unable to hold them in stable orbits, but the dark matter's gravity keeps everything bound together, maintaining the galaxy's integrity across its vast extent. The Milky Way rotates at about 168 miles per second, or roughly 605,000 miles per hour, at the Sun's distance from the center, a speed that seems incomprehensibly fast yet represents the steady, stable motion that has carried the solar system around the galaxy countless times over billions of years. This velocity is measured relative to the galactic center, tracking how fast the Sun and everything near it moves in its orbit around the galaxy's core. At this speed, the solar system is hurtling through space faster than anything humans have ever built, yet we feel no sense of motion because everything around us moves together. The Sun, the planets, the nearby stars, all carried along in the same vast rotation. The rotation isn't like a solid object spinning, where points farther from the center move faster. Instead, the galaxy exhibits what's called differential rotation, where different parts rotate at different speeds depending on their distance from the center and the distribution of mass at various radii. Near the galactic center, stars orbit more quickly, whipping around in just a few million years, while farther out toward the edge, rotation slows somewhat, creating a complex pattern of motion that reflects the galaxy's structure and mass distribution. This rotation has been ongoing for billions of years, a cosmic dance that began in the galaxy's youth and will continue far into the future, carrying stars and planets in their endless circuits around the galactic core. In just 1 hour, the solar system travels roughly 600,000 miles through space, a distance that equals about 2.5 times the distance between the Earth and the Moon, all while we go about our daily lives completely unaware of this tremendous motion. This calculation comes from the rotation speed of 168 miles per second multiplied by the 3600 seconds in an hour, giving a sense of the scale of motion involved in galactic rotation. To put this in perspective, in the time it takes to watch a television program or eat a leisurely dinner, our entire solar system has moved farther than any spacecraft has ever traveled, carried along by the galaxy's rotation like a leaf floating on a vast river. During an 8-hour sleep, the solar system travels nearly 5 million miles, and over the course of a year, the distance covered amounts to over 5 billion miles, distances so large they become difficult to visualize or comprehend. Yet this motion is smooth and constant, never changing noticeably over human timescales, so steady that only precise astronomical measurements can detect it at all. Ancient astronomers had no idea this motion was occurring, and it wasn't until the 20th century that technology became sophisticated enough to track these motions and understand the true dynamism of the galactic system within which we reside. This means that while you were sitting here for just a few minutes, you have traveled tens of thousands of miles through the galaxy, a journey made in total silence and without any sensation of the incredible speed involved. The Sun takes about 230 million years to complete one orbit around the galactic center, a period of time known as a galactic year or a cosmic year. Since the Sun and Earth formed about 4.6 billion years ago, the solar system has made this journey approximately 20 times, seeing the galaxy evolve and change through many cycles of stellar birth and death. One cosmic year ago, dinosaurs were first appearing on Earth, and 2 cosmic years ago, complex life was just beginning to diversify in the oceans during the Cambrian explosion. This immense timescale helps put human history into perspective, as the entire duration of human civilization represents only a tiny fraction of a single cosmic year, a mere moment in the long history of our solar system's journey through the galaxy. The center of the Milky Way, located about 26,000 light-years from Earth, contains a supermassive black hole called Sagittarius A*, a point of immense gravity around which the entire galaxy revolves. This black hole has a mass of about 4.3 million suns, yet it is concentrated into a region of space relatively small by cosmic standards, likely smaller than the orbit of Mercury around our Sun. While it is invisible because no light can escape its gravity, we can detect its presence by observing stars that orbit it at incredible speeds, whipping around an invisible point at millions of miles per hour. These stars, known as the S-stars, provide the definitive evidence for the black hole's mass and location, moving in orbits that only a supermassive black hole could explain. The environment near the galactic center is crowded and violent, with stars packed much more closely together than they are in our neighborhood and intense radiation filling the space between them. It is a place of extremes, where the massive gravity of the black hole shapes the lives and deaths of countless stars, and where gas and dust are drawn toward the center to be either consumed or expelled in powerful jets. Sagittarius A* is currently relatively quiet, consuming only small amounts of matter, but evidence suggests it was much more active in the past, perhaps glowing brilliantly as it swallowed vast clouds of gas and dust. This supermassive black hole is not unique to our galaxy. Almost every large galaxy is believed to have one at its heart, serving as a gravitational anchor and playing a crucial role in the galaxy's formation and evolution over billions of years. Around this central black hole is a dense cluster of stars, gas, and dust known as the galactic bulge, a region that glows brightly in the night sky toward the constellation Sagittarius. This bulge is shaped like a thick oval or a bar, and it contains some of the oldest stars in the galaxy, crowded together in a space where they are much more likely to interact or even collide than stars in the thinner disk where we live. The bulge stars orbit in more random directions than the orderly rotation of the disk, creating a complex swarm of stellar motion that astronomers are still working to map and understand in detail. The Milky Way spiral arms are not solid structures like the spokes of a wheel, but are rather density waves, regions where stars and gas are temporarily crowded together as they orbit the center. Think of a traffic jam on a highway where cars slow down and bunch up in one area before moving on. The jam itself stays in one place or moves slowly, even though individual cars are constantly entering and leaving it. In the galaxy, these density waves cause gas and dust to compress, triggering the birth of new stars and making the arms appear brighter and bluer than the rest of the disk because of the presence of short-lived, massive young stars. The main spiral arms are the Perseus arm and the Scutum Centaurus arm, which originate from the ends of the central bar, while several smaller arms and spurs like our own Orion arm also exist. These arms are the primary sites of star formation, where vast clouds of molecular hydrogen collapse under gravity to create new solar systems, ensuring that the galaxy continues to evolve and produce new generations of stars long after its initial formation. Between the arms, the density of stars is lower, and the space is filled with more diffuse gas and dust, creating a pattern that we see from our vantage point within the disk as a complex arrangement of bright regions and dark lanes. The dark lanes are caused by interstellar dust, tiny particles of carbon and silicates that absorb visible light and hide the stars behind them, much like smoke or fog can obscure a landscape on Earth. This dust is vital for the galaxy's chemistry, providing surfaces where complex molecules can form and eventually becoming the building blocks for rocky planets like our own. The Milky Way is currently consuming several smaller satellite galaxies, such as the Sagittarius dwarf spheroidal galaxy, through a process called galactic cannibalism. As these smaller galaxies orbit the Milky Way, our galaxy's immense gravity pulls them apart, stretching them into long streams of stars that eventually merge into our own stellar population. We can still see these stellar streams today, ghostly ribbons of stars that retain the motion of their original parent galaxies, acting as archaeological evidence of past mergers. This process has been happening for billions of years and is one of the primary ways the Milky Way has grown to its current size, incorporating the matter and stars of its smaller neighbors into its own structure. In about 4 billion years, the Milky Way is predicted to collide and eventually merge with the Andromeda Galaxy, our larger neighbor in the local group. Currently, Andromeda is moving toward us at about 70 miles per second, and while the distance between us is vast, about 2.5 million light-years, the collision is inevitable. Despite the name collision, individual stars are so far apart that they will likely never hit each other. Instead, the two galaxies will pass through one another, their gravity warping their shapes and eventually drawing them back together to form a single, massive elliptical galaxy sometimes called Milky Way. This future merger will trigger a massive burst of star formation as the gas clouds from both galaxies collide and compress, eventually resulting in a galaxy that looks very different from the spiral we inhabit today. This event will be a spectacular cosmic transformation, marking the end of the Milky Way as a distinct spiral galaxy, but also the beginning of a new, even larger chapter in the history of our local universe. The Milky Way is surrounded by about 150 globular clusters, ancient and dense groups of stars that orbit the galaxy in its outer halo. These clusters are among the oldest objects in the universe, containing hundreds of thousands of stars packed into a sphere only a few dozen light-years across, creating an environment where stars are thousands of times more crowded than they are in our part of the galaxy. Because they formed early in the galaxy's history, they are made primarily of hydrogen and helium and lack the heavier elements found in younger stars like the Sun, making them valuable laboratories for studying the early universe. These clusters act like a fleet of satellites, orbiting the main body of the galaxy in highly elliptical paths that take them far above and below the galactic disk, providing a three-dimensional perspective on the Milky Way's gravitational field. In addition to these clusters, the galaxy is surrounded by a vast halo of hot gas that contains as much mass as all the stars in the galaxy combined, though it is so thin and spread out that it is almost impossible to detect. This halo acts as a reservoir of material for future star formation, slowly cooling and falling into the disk over millions of years to provide the raw materials for new generations of stars. The Fermi bubbles are two massive structures of gamma-ray emitting gas that extend 25,000 light-years above and below the galactic center, discovered by the Fermi Gamma-ray Space Telescope in 2010. These bubbles are thought to be the result of a massive release of energy from the central black hole or a period of intense star formation millions of years ago, acting like giant exhaust vents for the galaxy's core. They serve as a reminder that the center of our galaxy is a place of incredible energy and activity, capable of producing structures that dwarf the visible disk of the galaxy itself. The Milky Way is not sitting still in the universe. It is moving toward a region of space called the Great Attractor at about 370 miles per second. This movement is part of a larger flow of galaxies within our local supercluster, Laniakea, as the gravity of massive concentrations of matter pulls on everything around them. Even on the largest scales, the universe is a place of motion and interaction, with galaxies and clusters dancing in a gravitational web that spans billions of light-years. As we conclude our journey through the Milky Way, we return to the quiet beauty of the night sky, where the soft glow of our galaxy reminds us of our place in this vast system. We are part of a grand cycle of birth, life, and death that has been playing out for billions of years, a story written in the stars and the spaces between them. The atoms that make up our bodies were once inside the hearts of distant stars, forged in the heat and pressure of stellar furnaces and scattered across the galaxy to eventually become part of us. We are truly children of the stars, and the Milky Way is our home, a vast and wondrous island in the cosmic ocean that continues to reveal its secrets to us as we look upward with wonder and curiosity. Stellar remnants like white dwarfs, neutron stars, and black holes are the final chapters in the life stories of stars, each representing a unique way that matter can be compressed by gravity once the fuel for nuclear fusion is exhausted. A white dwarf is the core of a star like our Sun that has shed its outer layers, a glowing ember about the size of Earth but with the mass of a star, so dense that a teaspoon of its material would weigh as much as an elephant. Over trillions of years, these objects will slowly cool and fade until they become black dwarfs, cold and dark remnants that no longer emit light or heat, though the universe is currently too young for any black dwarfs to have formed yet. Neutron stars are the collapsed cores of even more massive stars, crushed so tightly that protons and electrons merge into neutrons, creating an object only about 12 miles across but with more mass than the Sun. These objects can spin hundreds of times per second, acting as cosmic lighthouses known as pulsars as they emit beams of radiation that sweep across space with incredible precision. Black holes are the ultimate remnants, formed when the most massive stars collapse into a point of infinite density, creating a region where gravity is so strong that even light cannot escape. The galaxy contains hundreds of millions of white dwarfs, millions of neutron stars, and perhaps 100 million stellar mass black holes, most invisible or nearly so, contributing to the galaxy's mass but rarely revealing themselves through obvious signs. Occasionally, these remnants make their presence known dramatically, through novae when white dwarfs accrete enough material to trigger thermonuclear explosions on their surfaces, through X-ray binaries where material falling onto neutron stars or black holes heats to millions of degrees and radiates intensely, or through gravitational wave emissions when pairs of compact objects spiral together and merge. These exotic objects, born from stellar death, contribute to the ongoing cycle of matter and energy in the galaxy, returning processed material to the interstellar medium through various mechanisms and occasionally triggering new star formation through their violent events, ensuring that stellar death feeds stellar birth in the galaxy's continuous regeneration. As we drift towards sleep, let these thoughts of stellar remnants and cosmic extremes remind us of the vast and wondrous universe we inhabit, a cosmos filled with objects and phenomena that challenge our imagination and expand our understanding, each discovery revealing new depths to explore and new questions to ponder, in a universe that seems inexhaustible in its capacity to surprise and inspire us with its beauty, complexity, and the fundamental mysteries it continues to hold.